Gas chromatography, Rifqi, Andi and Syed Nazrin. Introduction. What is gas chromatography? GC is one of the most versatile analytical techniques in the laboratory. It is widely used for the determination of organic or volatile compounds. Gas chromatography diagram. How does gas chromatography works in animation? Gas chromatography apparatus.
Gas chromatography is a relatively fast and simple mechanism used to separate and analyze volatile gaseous compounds. All gas chromatographs share similar components: carrier gas flow controller, an injection port, an oven with a column, and a detector, which may include electrodes and a computer for analysis. We begin by injecting a small sample of liquid through a silicone-coated rubber septum. The substance then enters the injection port, which is kept at a constant temperature high enough to flash vaporize our liquid sample into a gas, but not so high that it will denature the sample. Once the substance is flash vaporized, a carrier gas carries our substance through the column. The most common carrier gases are hydrogen, nitrogen, and helium, of which hydrogen is the most common because it diffuses the solids more rapidly and also equilibrates between the mobile and stationary phases in the column. The rate of flow of our carrier gas can usually be adjusted with a knob in the machine, and most advanced apparatus may also be equipped with a split injection controller, which controls how much sample is processed and prevents overflowing of the column. Another helpful feature similar to split injection is temperature programming. With temperature programming, we can separate compounds with a wide range of boiling points and adjust the speed at which they go through the column. Packed columns are typically a glass or stainless steel coil that is filled with the stationary phase, or a packing coated with the stationary phase. In contrast, capillary columns are a thin fused silica in which the stationary phase is coated on the inner surface. Capillary columns provide much higher separation efficiency than packed columns, but are more easily overloaded by too much sample. Finally, the substance reaches a detector after it travels through the column. There are various types of detectors, such as flame ionization, electron capture, and thermal conductivity. The results are then obtained via a computer that reproduces the signals as they reach the detector. Each component produces a separate peak depending on their volatility and the amount of component present in the substance, which can be computed by calculating the area under each peak. Substances are separated based on volatility. For example, let's say we have a substance containing methyl, ethyl, and propyl substituents. The least carbon-containing substituents are the most volatile and will move through the column faster. As carbons increase, their volatility decreases and will elute later. Separation also occurs due to the polarity of the column or the type of column that is used. However, temperature or volatility are the most important features for separation. As each substituent reaches the detector, they will generate a signal, which helps create a chromatograph. Temperature programming is a useful technique commonly used when injecting a liquid that is a mixture. Let's say, for example, you have a mixture with substances A, B, and C. A and B have extremely low boiling points, and C has a relatively high boiling point. If this is true, our chromatograph would have two accurate tall and skinny peaks for A and B. However, C would generate a long, short peak, making it inaccurate. To adjust for this illusion problem, we would heat the mixture in the oven to the boiling point of the first two compounds, and after, say, about 10 minutes, increase the temperature to the boiling point of the other compound. The resulting chromatograph will then have all peaks as tall and skinny. By adjusting the temperature over time in the oven and column so that it will reach the boiling point of all compounds in the mixture in a much more accurate and rapid pace, we can calculate our results easier and faster.
How does gas chromatography works in real life? Gas Chromatography, Department of Chemistry and Biochemistry. Weigh the Cape vial. Simple explanation about gas chromatography in real application.
Hello, I'm Alex. I'm from the Max Planck Institute of Molecular Plant Physiology. We are interested in the substances inside plants. First, we dissolve them in a liquid. There we get a mixture of small particles and big particles. To separate them, we use gas chromatography. Gas chromatography is nothing but a tube. We put a small drop of our mix inside the tube. A gas stream is going through the tube. With heat, we evaporate our substances. We get a mix of small substances and big substances. Substances stick to the inner surface of the column, they go with the gas stream, and they stick again. Small particles stick less. This is why small particles come first to the end of the column, then intermediate, and big particles. This is how we separated them. We can precisely measure the time the particles need through the column. We know the time for specific particle sizes. Comparing this, we can estimate how big these particles are. And this is our column. The internal diameter is only 1/4 millimeter, and it's 40 meters long. The longer the better.
Directed by Rifqi, Andi and Syed Nazrin.